Sorry about that. I thought I was sharing so that you could be writing. Um, now you don't have to write this down. This is in a handout I gave you. But for some people, it helps to write it down. That's up to you which way you go. What we're going to be doing today is we're going to be dealing with stoichiometry and conversions. And the difference between the word conversion and stoichiometry is directly related to what we're working with. Stoichiometry is a type of conversions. Stoichiometry is specifically related to a chemical reaction, though. Whereas the word conversion is more broad, and it means anytime you're changing from one unit into another unit. But we're going to be dealing with stoichiometry today and chemical conversions. My goal after today and at least part of Tuesday is that you begin to recognize the pattern. You begin to be able to tell what you're supposed to do, when you're supposed to do it. And that's going to come in one of two ways. Number one, I will break down what we're working with as I do the problems. And hopefully, and if you can do it in that format, you're going to be better off in the future. If you can actually take the problem and break down based off of the words of the problem, what you're supposed to do. But until you get confident in that, you can use this flow chart. And it will help you to figure out what you need to do. Now, when I put together this flow chart, you'll notice that I listed substance A in purple, in blue, and substance B in red. You'll notice that basically when I'm talking about substance A compared to substance B, I'm talking about two things that have a different formula. And you'll notice the only way to go between two things that have a different formula, whoops, I missed an important piece. Is a mole to mole ratio. That is the absolute only way you can convert from one formula into another formula. Is you got to go through the mole to mole ratio. And there's a couple of different ways that we can get this mole to mole ratio, and it's really dependent upon what we're working with. Are we simply working with an element within a compound? If you're simply working with an element in a compound, the mole to mole ratio is going to come directly from the chemical formula itself. The other location where we can get the mole to mole ratio, as I showed you on Tuesday, is from the coefficients of the balanced chemical equation. You'll use the coefficients of the balanced chemical equation anytime you're converting from one substance in a chemical reaction to another substance in the chemical reaction. So in other words, that second variation is related to using a chemical reaction. Now, some of the things that you'll note, anytime, and I've said this before, anytime I've used the word atoms, ions, and molecules, I automatically go to Avogadro's number as a conversion factor I'm going to need. Because that's the only way, that's the only conversion factor that has the words atoms, ions, or molecules in it, is Avogadro's number. Anytime, and that's true whether we're talking about substance A or whether we're talking about substance B. Again, if I see the word atoms, ions, molecules, your first thought should be, I gotta use Avogadro's number. Anytime you see grams, no matter whether it's grams of A or grams of B, you will notice that the conversion factor is the same. You need the molar mass for that substance. So anytime I see grams, I automatically go, okay, I'm going to need the molar mass. And then, like I said, anytime I see two different formulas, I automatically go, okay, I'm going to need a mole to mole. Because that's the only way to convert between two different formulas. I just got to figure out, at that point, I just got to figure out where my mole to mole is going to come from. Okay. Again, you have this on I gave you this flow chart somewhere else. Now, like I said, I am going to do it where I simply break apart what I've been given and break apart what I need to solve for. And in breaking it down, it's going to tell me what conversion factors I need. But if you're not there, you can use this flow chart. And it'll help you figure out what conversion factors you need. Let's just look at an example. many moles of hydrogen can be formed when 3.22 moles of aluminum react with excess hydrobromic acid according to the equation, or according to the reaction, of 2 aluminum plus 6 HBr goes to make 2 aluminum bromides plus 3 hydrogens. Okay, I'm going to break it down. First thing I'm going to do is identify what I have been given. I have been given 3.22 moles of aluminum. By the way, MOL is short for mole. So, and that is not just my notation, that is anybody I know and everybody I know, they'll use MOL for moles. I'm going to identify what I need to solve for. I have been asked for moles of hydrogen. Now I'm going to break it down. The first thing I notice is that I have 2 different substances. If you have 2 different substances, the only conversion factor, or you're going to need the mole-to-mole ratio. And it's going to come from the balanced chemical equation. According to this balanced chemical equation, 2 moles of aluminum react to form 3 moles of hydrogen. The next thing I'm going to do is I am going to look at the units. Well, I need moles of aluminum. That's not a problem. I already have moles of aluminum. And I'm going to do the same for the products. I need moles of hydrogen, not a problem. I've already got moles of hydrogen. So I'm only going to need 1 conversion factor in this particular case. So I'm going to start with the information I was given. And I am going to use the conversion factor I need. Now, of that mole-to-mole ratio, the 2 moles of aluminum must go in the denominator with the 3 moles of hydrogen in the numerator. The reason that the 2 moles of aluminum must go in the denominator is because the unit and the substance must cancel out, leaving moles of hydrogen. Since that is what I wanted to solve for, I'm ready to key it into the calculator. and I get an answer of 4.83 moles of hydrogen. Double checking my significant digits, I started the problem with 3 significant digits. Mole to mole ratios, no matter where you get them from, they are exact quantities. And so they're going to have an unlimited number of significant digits. Since the measurement with the fewest had 3 significant digits, our answer should have 3 significant digits. So we would report it as 4.83 moles of H2. Let's look at another example. How many grams of HF can be formed when 0.25 moles of hydrogen reacts with excess boron trifluoride according to the reaction two boron trifluorides react with 3 hydrogens to make 2 borons and 6 hydrofluoric acids. Okay, let's break this down. Let's start with what we were given. We were given 0.25 moles of hydrogen. We identify what we were asked to solve for. We were asked to solve for grams of HF. Now we break it down. The very first thing is that we are dealing with 2 different formulas. 2 different formulas means you're going to need a mole to mole ratio. This one is going to come from the balanced chemical equation, which says 3 moles of H2 produce 6 moles of HF. Continuing to break this down, the next thing I notice is I need moles of hydrogen. That is not a problem. I already have moles of hydrogen as a unit. The last thing I note, though, is I need grams of hydrogen fluoride. Grams means I'm going to need the molar mass. So I have 1 hydrogen at 1.008, and I have 1 fluorine at 17, 19. 19.00. So that's 1.008 plus 19.00, meaning that we're dealing with 20.008. That is going to be 20.008 grams of HF is 1 mole of HF. This comes back to our molar masses we learned to calculate. Okay, now that I've broken down what I have and what I need to solve for, let's begin. And I have determined conversion factors. I'm ready to start this problem. 0.25 moles of H2. The first conversion factor I need is going to have moles of H2 in it. So I'm going to use the mole to mole ratio of H2. The moles of H2 portion of that mole to mole ratio goes in the denominator, while the moles of HF go in the numerator. We place the moles of H2 in the denominator so that the unit and the substance would cancel out, leaving us moles of HF. Well, I have the correct substance, but I need grams. So my next conversion factor is going to contain the molar mass. I'm going to place the mole portion in the denominator with the mass portion in the numerator. I placed the mole portion in the denominator so that the unit and the substance would cancel out, and I'm left with grams of HF, which is what I was asked to solve for. Keying this into the calculator, you get a value of 10.004 grams of HF. Now, looking at significant digits, we started with 2 significant figures in our moles. The mole to mole ratio is an exact quantity, and therefore it has an unlimited number of significant digits. Our molar mass, the mass portion has 5 significant figures, and the mole portion of a molar mass has an unlimited number of significant digits. Looking at this calculation, the measurement with the fewest had 2 significant digits, so our answer can only have 2 significant digits. So I would report this answer as 10 grams of HF. Questions? Yes. Exam 4 will contain molar mass. It will contain conversions of elements within compounds. It will contain balancing chemical equations. And yes, it's going to contain these stoichiometry conversions. One of my goals today, and well, actually I'm going to do it this weekend, but hopefully by Monday I'll also have the answer key up, is I am going to put up a couple of new, I'm going to put up some problem sets, but I'm also going to develop some new problem sets so that they're all mixed up like they would be on a test. And that way you can get a better idea. Now, we do have one more topic besides this stuff that's going to be on the exam. Let's look at another example. Let's figure out how many molecules of sodium chloride can be formed when 20.0 grams of copper 2 chloride reacts with excess sodium nitrate according to the reaction. CuCl2 plus 2NaNO3 goes to make CuNO32 plus 2NaCl. Oh, there, I've lost the grams up here. I just realized that. I said them, but I did not write them. Okay, we are going to look at what we were given. We were given 20.0 grams of CuCl2. We are going to look at what we were asked to solve for. We were asked to solve for molecules of NaCl. Okay, let's break it down. First thing I notice is we're dealing with two different substances. Two different substances means I'm going to need a mole-to-mole ratio. According to the balanced chemical equation, 1 mole of CuCl2 produces 2 moles of NaCl. Next thing I notice is I am dealing with grams of CuCl2. Grams means I'm going to need molar mass. I have 1 copper and I have 2 chlorines. Copper has a mass of 63.55 and chlorine has a mass of 35.45. So the copper contributes 63.55 to the molar mass. The chlorines contribute 70.90 to the overall molar mass. So adding those together, you get a value of 134.45. That is 134.45 grams CuCl2 equals 1 mole CuCl2. Continuing to break down this formula, the next thing I see is I need molecules of NaCl. Molecules means I'm going to be using Avogadro's number. Which is 6.022 times 10 to the 23rd, in this case, NaCl molecules. Will equal 1 mole of NaCl. Folks, one reason I color code this is so hopefully if you rewatch the video, it will, you can see where I'm going with each piece. And it's up to you whether you bring in colored markers and color and highlighters on the test. That's up to you if it'll help you. Okay, now that I have broken everything down, I'm ready to perform this conversion. I'm going to start with the 20.0 grams of CuCl2. My first conversion factor must have grams of CuCl2 in it. So therefore, I'm going to use the molar mass. With the molar mass, the 134.45 grams of CuCl2 will go in the denominator, with the 1 mole of CuCl2 going in the numerator. We had to place the grams of CuCl2 in the denominator so that the unit and the substance would cancel, leaving moles of CuCl2. Now that I have it in moles of CuCl2, I need a conversion factor that has moles of CuCl2 that I haven't used. So I'm going to use the mole to mole ratio. The 1 mole of CuCl2, whoops. The 1 mole of CuCl2 will go in the denominator, while the 2 moles of NaCl go in the numerator. We place the 1 mole of CuCl2 in the denominator so that the unit and the substance would cancel, leaving moles of NaCl. Now I've got it into the substance that it requested. I just got to get it into the unit that it requested. So therefore, I'm going to convert this moles of NaCl into molecules of NaCl, and I'm going to do so using Avogadro's number. With Avogadro's number, the 1 mole of NaCl is going to go in the denominator, and the 6.022 times 10 to the 23rd NaCl molecules will go in the numerator. We place the moles of NaCl in the denominator so that the unit and the substance would cancel out, and leaving you the molecules of NaCl. Now I'm ready to key this into the calculator because I have achieved what it was asking for, which was molecules of NaCl. And when I key this into the calculator, the answer that I get is 1.7916 times 10 to the 23rd NaCl molecules. Now I do have to pay attention to significant digits. My starting quantity has 3 significant digits. The molar mass, the mole portion is going to have an unlimited number of significant digits, while the mass portion has 5 significant digits. Mole to mole ratios are exact quantities, therefore they have an unlimited number of significant digits. The Avogadro's number, the numerator has 4 significant digits because it has 4 digits in the mantissa of the scientific notation, while the mole portion has an unlimited number. Looking at this math, 3 significant digits is the minimum. So therefore, my answer should have 3 significant figures. So the answer I should actually record for this is 1.79 times 10 to the 23rd NaCl molecules. Okay, I want you to keep this problem where you can pay attention to it, but I'm going to scroll to the top of the screen. Okay, I want you to look at the railroad track. We started with grams of CuCl2. What was our first conversion factor? It was the molar mass, correct? The first conversion, we started with grams, but what was the first conversion factor? So that meant there was a numerator and a denominator.
Molar mass.
The molar mass. What was our second conversion factor? Mole-to-mole ratio. What was our third conversion factor? Avogadro's number. And we wound up with molecules of a new compound. So again, if you can't break it down like I've been doing, this will help guide you. And you'll notice molar mass, okay? We calculated molar mass. The mole-to-mole ratio, because we were dealing with the 2 substances in a reaction, we used the coefficients of the balanced equation. And then Avogadro's number. The only other thing about those conversions was knowing what went in the numerator and what went in the denominator. And if you'll notice, whatever was in the numerator in the previous part was in the denominator in the next part. So it always went, always bounced. So that it was always canceling out whatever was in the previous part. Those are just some things that I wanted to make note of so that you have that information. And hopefully you could see it. And now let's go back to the second problem. Let me remember what the second problem was. Second problem was grams of HF from moles of H2. We started with moles of H2, so we're starting here on this one. What was our conversion factor? Our first conversion factor in that second problem. The mole-to-mole ratio. What was our second conversion factor in that problem? Molar mass. So I started with moles of copper to fluoride, and I went to grams of sodium fluoride. And those were my conversion factors. We could go back to the beginning one too and do the same thing, but you would see the same process. So in other words, what I am trying to say is if breaking it down does not work for you, you can rely on this. Now you have to memorize this. I'm not giving it to you, but you can rely on this to help you know what to do when. Okay, let's look at another problem. But before well, no, I'll do that in the next one. Okay. How many grams of oxygen are needed to form 12.625 grams of water? According to the equation, where 2 ethanes are burned in the presence of 7 oxygens to form 6 waters and 4 carbon dioxides. Okay. We identify what we were given. We were given 12.625 grams of water. We identify what we were asked for. We were asked for grams of oxygen. Now we break it down. Water, oxygen, different compounds. Anytime the compounds are different, you're going to need the mole to mole ratio. So you're going to convert, so you're going to need to know that there are 6 moles of water that are formed from every 7 moles of oxygen that are used. The next thing is grams of water. Anytime I see grams, I know I need the molar mass. There are 2 hydrogens at 1.008. There is 1 oxygen at 16.00. So 2.016 and 16. Add those together, that means water is 18.016. That's 18.016 grams of water is equal to 1 mole of water. Continuing to break this down, the next thing I see is I'm going to need grams of oxygen. That means I need the molar mass. Anytime I see grams, it means I need the molar mass. There are 2 oxygens at 16.00 each, meaning it is 32. That is 32.00 grams of oxygen is equal to 1 mole of oxygen.
Now that I've broken it down, I'm ready to begin this math. So I have 12.625 grams of water. My first conversion factor needs to have grams of water. Therefore, I'm going to use the molar mass of water. So 18.016 grams of water is going to go into the denominator, while the 1 mole of water goes into the numerator. We had to place the grams of water in the denominator so that the unit and the substance would cancel, leaving us moles of water. Now we're going to convert the moles of water into moles of oxygen. We're going to do so using the mole-to-mole ratio, which says that there are 6 moles of water formed for every 7 moles of oxygen used. We place the moles of water from the mole-to-mole ratio in the denominator so that the unit and the substance can cancel, leaving moles of oxygen. But we were asked for grams of oxygen, so we're going to use the molar mass of oxygen. We're going to place the 1 mole of oxygen in the denominator with the 32.00 grams of oxygen in the numerator. We placed the 1 mole of oxygen in the denominator because we needed the unit and the substance to cancel. Now we have grams of oxygen and we're ready to do our mathematics. And when you key this into the calculator, you get a value of 26.1619 grams of oxygen. Now we need to pay attention to significant digits. Our starting quantity had 5 significant digits. The molar mass for water, the mass portion has 5 significant digits, while the mole portion has an unlimited number of significant digits. Mole-to-mole ratios are exact quantities, and therefore they have an unlimited number of significant digits. The mass portion for the molar mass of oxygen has 4 significant digits, and the mole portion has an unlimited number of significant digits. Looking at this calculation, since it is multiplication and division, that means that we will use the fewest significant digits, which is 4. So our answer should only have 4 significant digits, and so you would report your answer as 26.16 grams of oxygen. Questions?
This might just be a question, but you're not going to trick us. We don't have to check the formula to make sure it's balanced, do we?
Okay, so the answer to your question. On an exam, I have a separate molar mass question. So I would have given you the molar masses in this question. On the exam, you will have a separate balancing chemical reaction. So I will give you the balanced chemical equation for this problem.
Gotcha.
That way, I don't have to worry about compounding errors. If you make a mistake balancing, it's not going to impact the rest of the problem. So they are separated problems.
Gotcha.
So no, I'm not going to trick you.
Yeah.
I mean, technically, you should always make sure the equation's balanced. But like I said, I'm not going to trick you because I don't want to worry about compounding errors. other questions? Yes.
How are you gonna grade these? Like, is it how our past exam was, or no, the one before that, where she did the whole one thing wrong?
This one, this is the test where I'm really able to do partial credit. So showing your work is extremely vital. Because if all of your work is correct and you just get the answer wrong, you're only looking at 1 or 2 points off. If you miss a conversion factor, usually, so let's say this problem was worth, we'll go with 10 points. It wouldn't have been 10, it would have been, let's say 7, or no, 8 points. This conversion factor, I would give 2 points. So if you got it right, you would get 2 points. This conversion factor, I'd give 2 points. So if you got it in there and it's correct, it's got to be lined up correctly too. You'd get 2 points. 2 here. And then the answer is also 2 because this, whoops, not that. This is worth 1 to 2 points. Actually, I think what I would do is it would be 9 points. I always have to figure it out. It's 9 points. So it's 1 point for answer, 1 point for significant digits, and 1 point for unit and substance. And that's how the 9 points would be distributed. So you get partial credit on these problems. Yes. I have to look at your syllabus. I can't remember if it's Tuesday or Thursday prior to spring break, or prior to finals week. Usually I make it the Tuesday so that I can pass them back on Thursday. And you know where you stand before finals. So that would make sense that it was on Tuesday. Yeah, the 22nd is a Tuesday. I just can't remember for certain if it was the 22nd or 24th. I have to look at your syllabus, but it's not next week, but the following week. Questions? You're getting into my head early about how to do these problems, which is fine. Okay. Let me give you one to do. How many moles of aluminum hydroxide are produced from 4.2 grams sodium hydroxide reacting with excess aluminum hydroxide. No, excuse me, aluminum sulfite. According to the reaction, Al2SO33 plus 6 NaOH goes to form 3 Na2SO3 plus 2 AlOH3. And if you don't have your periodic table, I will say sodium is 22.99. Oxygen is 16.00 and hydrogen is 1.01 is the one they gave, actually. I've been using 1.008, but Okay, let's look at the answer and the process and all that jazz. So I identified what I was starting with. I was starting with the 4.2 grams of NaOH. I identified what I wanted to solve for. I wanted to solve for moles of aluminum hydroxide. After I wrote that down, I then started breaking it down. I noticed that my starting substances were different, so that told me I was going to need the mole to mole ratio. I noticed that I had grams of sodium hydroxide, so that meant I was going to need the molar mass of sodium hydroxide. And then I noticed that I needed the moles of aluminum hydroxide, which are already in the mole to mole ratio. So that meant I only needed 2 conversion factors. And so I took the 4.2 grams. I used the molar mass first, and I put the mass of sodium hydroxide in the denominator so that the unit and the substance would cancel. That left moles of sodium hydroxide. I then used the mole to mole ratio of sodium hydroxide to aluminum hydroxide to convert that into moles of aluminum hydroxide. Since that is what I wanted to solve for, I completed this calculation and I got 0.035 moles of aluminum hydroxide. I did check my significant digits. I started out with 2 significant figures. The mole to mole rate, the molar mass, the mass has 4 significant figures, while the mole portion is an unlimited number. Mole to mole ratios are exact quantities with unlimited number of significant digits. So since the measurement with the fewest had 2 significant digits, my answer was only allowed 2 significant digits. And so that was the answer. Questions? Oh, there's not time to start another problem. These aren't short. The only way to get fast at them is to do them. And then you'll get faster and faster and faster. I will be putting together a homework that is due next Tuesday. I'll try to get it done tomorrow at the latest. And it will include some of these calculations. And it will also include balancing chemical reactions. That is going to be the main focus of the next active homework. Any questions for me? We'll do a few more of these on Tuesday. And then we're going to start talking about solutions. And we're going to talk about molarity, what it means, and get into some calculations using molarity. So that will be our Tuesday and Thursday of next week. I will see you next week.